All informational criteria are realized in physical processes that place physical criteria on aspects of energy. In the case of neurons, the primary physical mechanism that places physical criteria on aspects of energetic inputs is that which determines whether summed potential at the axon hillock surpasses the critical threshold above which an action potential will be generated. One might say that summation of excitatory and inhibitory postsynaptic potentials, EPSPs and IPSPs, whether in a dendrite or later in the soma, cannot itself comprise an assessment of information because the summation is purely mechanistic. Potential just goes up or down and either passes the action potential threshold or not. When a neuron is considered in isolation of all the neurons that give it input, this is correct. A neuron made to fire alone in a petri dish realizes and conveys no information. One could depolarize the neuron and it would fire once the threshold was passed. In a localistic sense, then, summation of potential at the axon hillock cannot be regarded as placing any criterial conditions on the informational content of the input into a neuron. Similarly, a neuron cannot be thought to assess information criterially when considered in isolation. It just takes chemicals such as glucose, oxygen, neurotransmitters, and ions as inputs. But if the threshold for firing is met, if and only if certain kinds of informational facts are true about the inputs, then the mechanism underlying neuronal firing not only assesses net potential at the axon hillock, it also assesses these informational facts. In this way, physical criteria placed on physical inputs can realize informational criteria placed on informational inputs. Thus, the information realized in neural firing is not realized solely in its firing. It's realized in its firing given inputs defined by its pattern of neuronal connectivity within a circuit of neurons. This is an inherently holistic or globalistic view of informational realization or mental activity. It runs counter to the dominant reductionistic bias of both science and Western culture. A simple cell in primary visual cortex provides a straightforward example of how this might be done more generally. A simple cell in cortical area V1 fires if a luminance-defined edge or bar of light is present at a given location in the visual field. Here, you can see an example of a simple cell recorded by the neurophysiologists David Hubel and Torsten Wiesel. They argued that a simple cell could be wired up by having earlier detectors that themselves responded best to a spot of light all converge on a downstream neuron, namely the so-called simple cell, which would only fire if it received simultaneous action potentials from a subset of these earlier cells. These earlier cells, found in a part of the brain called the lateral geniculate nucleus of the thalamus, feed into V1. They tend to be excited by light falling on one spot on the retina, and to be inhibited by light falling around this spot. These neurons are said to have an excitatory center and an inhibitory surround receptive field or response field, which is just that part of the retina that leads to a change in the cell's responses. A simple cell could be constructed that fired if, say, at least 3 out of 5 on-center off-surround neurons triggered EPSPs in the simple cell within that cell's very brief temporal integration window. If these center-surround cells respond to inputs from adjacent regions of the visual field that fall along a line, as shown here, the simple cell fires when a band of light of a particular spatial extent and orientation appears at a particular location in the visual field. The axon hillock in this simple cell places physical criteria on net potential within a cell before physical firing is triggered, and simultaneously places informational criteria on informational inputs for the realization of certain information, namely the presence of a bar of light, that occurs when the simple cell fires. The simple cell functions as a coincidence detector in that several lower-level facts, that is, inputs from lateral geniculate neurons, must hold at the same time before it fires above its baseline firing rate. Coincidence is not made of energy in addition to the energy it is realized in. That is, coincidence per se does not have mass or momentum or other attributes of an amount of energy. For example, several temporally coincident action potential inputs are not made of more energy than a staggered sequence of the same number of action potentials. But coincidence detection affords the possibility of detecting spatial patterns that exist at a given time. And these spatial patterns, or spatial relationships among inputs, are likewise not made of energy in addition to the energy in which the pattern is realized. Just as the fact of temporal coincidence has no mass, orientation also has no mass. Coincidence detection therefore allows neurons to respond to relationships among material inputs. By coming to encode arbitrary relationships among light, sound, heat, or vibration energy detected locally at the sensory sheet, neurons make explicit information about such relationships that are only implicit in the sensory input. An eliminative reductionist might want to fight back by arguing that the assessment of informational criteria is epiphenomenal upon the assessment of physical criteria for neuronal firing. But physical neurons are arranged such that physical criteria for firing are satisfied only when certain information is the case, so that an animal can gain information about its environment and body in order to be able to respond to things and events appropriately. Since evolution operated on perceptual, motor, and cognitive systems to optimize information processing, one could equally well argue that the particular physical implementation of informational realization that we find in brains in the form of action potentials within neural networks is arbitrary and therefore epiphenomenal upon the information that needs to be realized so that an animal can see, eat, flee, and mate successfully. A given physical criterion for firing, given by summation of potential at the axon hillock, can realize different informational criteria depending on the connectivity modulated by synaptic weights and other synaptic properties at a given time. For example, given one set of inputs, a simple cell in V1 might fire to a bar of light in one location. But if its inputs change suddenly, it might fire to a bar of light at a slightly different retinotopic location, or even to a bar of light at a different orientation. Neural connectivity cannot change rapidly because axons cannot suddenly grow within milliseconds, but effective neural connectivity can change very rapidly by changing synaptic weights within milliseconds. Let's say that a simple cell now does not receive inputs from 5 spot of light detectors, but from 25 such cells. We can turn the weights of most of these inputs down to 0 and have some inputs be set to 1. For the presynaptic neurons whose weights are set to 0, even if they fire, they can't depolarize the postsynaptic neuron. The ones whose weights are set to 1 can depolarize the postsynaptic neuron. Now imagine if we can rapidly change synaptic weights from this pattern of synaptic weights to this pattern, or this pattern. Even though the overall pattern of axonal connectivity has not changed, the effective pattern of connectivity has changed, since now different presynaptic neurons drive the postsynaptic cell. I call such changes in epiconnectivity rather than connectivity. This is why I think that learning about the pattern of axonal connectivity, known as connectomics, is not going to get us very far in unraveling the neural code. We will also need a new field of epiconnectomics if we are to make deep headway in understanding how mind is realized in matter. The physical criteria for firing at the axon hillock do not change, but the informational criteria for firing change as a function of epiconnectivity. Epiconnectivity can change via extremely rapid dynamic changes in synaptic weights due to the opening or closing of ionotropic receptor pores, and slower changes in synaptic weights that depend on protein synthesis via, for example, long-term potentiation. It seems trivial to say that neurons process information, but how do they carry information at all? Neurons carry, communicate, compute, and transform information by transforming action potential spike inputs into spike trains sent to other neurons. If I say, "Please pick up your coffee cup," and you do, then a pattern of air vibrations has been transduced into neural firing in nerves that receive inputs from inner hair cells. This in turn is transformed multiple times across neuronal subpopulations until the meaning has been decoded at the level of words and a proposition, allowing you to issue a motor command to carry out my request, perhaps after having considered various other possible courses of action. This can all happen in less than a second after hearing the word cup. To try to cut information and meaning out of the causal picture here, as radical reductionists and epiphenomenalists do by arguing that there are only particles interacting with particles, makes a fundamental error. Of course there are only particles interacting with particles, but assuming ontological indeterminism, countless sets of particle paths could physically follow my command, given your initial physical state and the physical state of the world at the moment of the word cup. Why did a subset of possible particle paths occur that was consistent with an information processing view of the brain and not other physically allowed sets of particle paths that would have been consistent with the indeterministic laws of particle physics, but not consistent with an information processing account? Because neurons place physical criteria for firing on inputs that are also informational criteria on inputs, such that only those subsets of possible particle paths that meet those criteria can occur, only those subsets trigger neuronal firing. On this account, mental events can cause future mental and physical events by altering physically realized informational criteria for firing that can be met by future neuronal inputs. Informational criteria for neural firing are realized in physical criteria for firing within a neuron and, at a higher level, by a neuron existing within a neural circuit such that it only deviates from its baseline firing rate if certain informational facts are true. We consider the case of a simple cell that fires above its baseline firing rate if and only if a bar of light occurs at a particular position on the retina or in the visual field. We can imagine other neurons that fire if and only if a cat is visible. Such neurons, in fact, exist in the anterior inferotemporal lobe. Firing alone in a petri dish, such a neuron would not be a cat detector. But given the right set of neural inputs, we can create a cascade of ever more complex feature detectors, from bar detectors like simple cells to shape detectors and ultimately cat detectors. Even though an individual neuron is dumb, when linked in a cascade of simple if-then statements realized in neural circuits, neurons can become smart. When a cat-detecting neuron fires, the rest of the brain learns that a cat is present in the sensory input and can act on this information. I have argued that top-down causation in general, and mental causation in particular, occurs because physically realized informational criteria effectively carve out from among all sets of possible paths open at the particle level, an instance of that tiny subset that is also an informational path or causal chain. This is only possible because neurons physically realize informational criteria, and this, in turn, is made possible by the discrete summation of potential within neurons, which is, in turn, only possible because there is a synaptic cleft that keeps the potential from one neuron from contaminating the potential in another neuron. Thus, mental causation is possible because of the 20 to 40 nanometer synaptic cleft.